May I now request Dr. Pushpalata HL, HOD Physics, to welcome the participants to this national.
Thank you, Sandhya. Good morning, everyone. It gives me an immense pleasure to welcome all of you to this national webinar on two-dimensional materials for diverse applications. I wholeheartedly welcome today's speaker, Dr. Pratap Vishnoi, Material Research Laboratory, University of California, Santa Barbara, USA, to this webinar. I welcome you, sir. I'm very much honored. Thank you, sir. I'm very much honored to welcome our dynamic leader, Sri D.K. Mohan, Chairman, Cambridge Group of Institutions, Bengaluru, to this webinar. I welcome you, sir. I'm very much delighted to welcome our beloved principal, Dr. Suresh L., Head of Cambridge Institute of Technology, who is the backbone of this program. Welcome you, sir. I heartily welcome Dr. Shanti S.R., Dean Basic Sciences, HODs of various departments, and my dear faculty colleagues to this webinar. Welcome you all. Last but not the least, I'm very happy to welcome all the participants and my dear students who are eagerly waiting for listening to the today's speaker, Dr. Pratap Vishnoi. Welcome you all. Thank you, one and all.
Thank you, Professor Pushpalata, for your welcome address. Now I request my colleague, Professor Manjunath Yes, who is the chief convener of this webinar, to give his introductory remarks.
Good morning, everybody. Respected Principal Dr. Suresh L. and respected Chairman, Cambridge Group of Institutions, Bengaluru, D.K. Mohan sir, and then respected Dean Madam, Dr. Shanti S.R., Dean Basic Sciences. And I also welcome all the heads of the departments. I take this opportunity to put forward the thoughts and views, how we have designed and how we came at this very beautiful national webinar. During the times of COVID, we all stay at home and stay safe. So we thought of organizing some national webinar on contemporary hot research topics. Then we thought of organizing two-dimensional materials for diverse application. I am very happy that for this national webinar, which has been organized from the Department of Basic Sciences and Cambridge Institute of Technology, Bengaluru, for this national webinar, nearly more than 1,300 participants have registered, not only from Karnataka, all over the India, from different states. We have got responses from different universities of the country. If I can read the universities: Andhra University, Maharishi Dayanand University, Cochin University, Chandigarh University, Jadavpur University, Geetham, Satyabama University, PES University, Sharnbasva University, Annamalai University, JN University, Thiruvalluvar University, Pondicherry University, University of Kashmir, University of Madras, Vellore Institute of Technology, and SRM Institute, Madras or Chennai. And also we have got the responses and registrations from across the country, from different states, different cities. I'm very happy to see them virtually in this single platform under the umbrella of Department of Basic Science, Cambridge Institute of Technology, Bengaluru. So we College of Karnataka, which has been affiliated with VTU, have also registered and now they have participated. I am very happy. VTU physics teachers group also, through that our WhatsApp link got propagated like anything. So even now we are getting registrations. And apart from engineering colleges, we have got participants from IIIC, Indian Institute of Science, IIT Bombay, JNCASR, and then CSIR laboratories and other R&D institutes. Received registrations from Oman, and then USA, and then Taiwan, and other countries also. So this is the brief overview of this national seminar. And coming to today's speaker, Dr. Pratap Vishnoi. He is my intimate friend, and he is doing extremely well in science, especially R&D, that too especially in 2D materials. I'm very happy to read out his profile. He is from Rajasthan, Bikaner, and we both worked under the guidance of Bharata Ratna C.N.R. Rao, and he was working for his postdoctoral work, and I was working for my PhD. So, and we both of them collaborated and we have worked on 2D materials, and I have many papers with him. I'm very happy to read out his profile. Chemistry from IIT Mumbai, and then he has got Master of Science in Chemistry, Rajasthan University, Jaipur, and he got Bachelor of Science, CBZ, at MLB Government College, Bikaner University, Bikaner, and postdoctoral fellow with Professor Murugavel, and also postdoctoral fellow Professor C.N.R. Rao, and postdoctoral fellow presently with Professor Ram Sheshadri and Professor Sir Anthony K. Cheetham, University of California, Santa Barbara, United States. And his research interests are organic, inorganic, hybrid materials, and nanomaterials. He has got vast research expertise. He has worked on synthesis and characterization of perovskites, layered nanomaterials, metal organic frameworks, covalent organic frameworks and metal complexes, hydrothermal, solid state and solution phase synthesis of materials, liquid exfoliation and chemical functionalization of 2D materials, especially MOS2 and phosphorine, optical properties, fluorescence-based chemosensing, single crystal XRD, and he has got many awards and fellowships. DST postdoctoral fellowship overseas in nanoscience and nanotechnology, Sheikh Sakar Laboratory postdoctoral fellowship, DST postdoctoral fellowship in nanoscience and nanotechnology, and travel grant from IIT Bombay for international conference. And he was a senior research fellow, CSIR Government of India. And he has secured first rank in MSc Chemistry. And he has presented his research work in various international platforms. International Conference on Nanoscience and Nanotechnology, ICONSAT Bengaluru. And then he has made various poster presentations also. And he has attended many workshops, and he has given many invited talks. He has got teaching experiences, and he has been affiliated with various professional organizations, life member of Material Research Society of India, Chemical Research Society of India, associate member of Royal Society of Chemistry and Material Research Society, so on and so forth. And he has got many publications, and he has received more than 500 citations. Apart from this, I'm extremely happy that he's not only a very good scientist, but I can say that he's a very good human being also. And he's highly professional in terms of scientific research. He follows almost all ethics. So I take this opportunity once again, welcome all the participants from across the country, from different universities, different engineering colleges, and different R&D institutes. And I also welcome the participants from the abroad. This was the overview of the national. I also thank our beloved principal, Dr. Suresh L, and respected chairman, Sri T.K. Mohan, and our beloved Dean Basic Sciences, Dr. Shanti SR, and my esteemed colleague and head of the Department of Physics, Dr. Pushpalata HL, for giving this opportunity. I hope you will enjoy this national webinar and you will take inputs regarding the two-dimensional materials. Thank you, one and all.
Thank you, Professor Manjunath. It is indeed a matter of honor and pride for us Cambrians to witness the webinar by Dr. Pratap Shenoy. Any event becomes successful only if it is properly planned, considering the consensus and willingness of its team members. Such a team is led by a Dean, Basic Sciences, Dr. Shanti SR. I request Dr. Shanti to deliver the keynote address.
Good morning to one and all present here. Welcome you all for this national webinar. Building new relationship and meeting new contacts is important to each and everyone's personal and professional life. We the Department of Basic Science created one such opportunity to meet you all on the virtual platform to gain the knowledge on two-dimensional materials for diverse applications by Dr. Pratap from University of California. From Professor Manjunath introduction, we came to know that the high profile of Dr. Pratap, who is a great orator, a good speaker, and doing great work on R&D. So, happy to inform you that 1,300 participants across the globe have registered for this national webinar. We all are waiting for information and knowledge which you are going to share with us in today's program. I hope all the participants who have registered for this national webinar will enjoy the session. I thank our Honorable Chairman, respected Principal, beloved CEO for the encouragement and the support in conducting this program. Thank you, one and all.
Thank you, Dr. Shanti, ma'am, for your address. Now we start the most awaited session, that is a presentation by our guest for today, Dr. Pratap Shah, on the topic two-dimensional materials for diverse applications. And now I request Dr. Pratap Shenoy to please give his presentation. Over to you, sir.
Well, thank you very much. This is a fantastic webinar. And I'm delighted that, in the midst of such a crazy pandemic, if we have such a seminar, this, no other day is better than this. And I'm very excited to do this. Let me thank convener Professor Manjunatha for, a wonderful introduction and showing me that, how huge this webinar, there's a large number of participants and, different areas and students and others, and the interests which we all have in, such areas which are currently in the forefront of science and technology. I thank Head Department of Physics, Dr. Pushpalata, Dean Basic Sciences, Dr. Shanti, Principal Dr. Suresh for organizing such a beautiful webinar, which is indeed a pleasure to be part of. So let me start by saying thank you all those who are taking part in that, and I'm so excited to talk in this area. And the subject which is very dear to me. Yeah, so the subject called two-dimensional materials is very dear to me. I have worked a lot on this area in Bangalore, and I'm working here too. So in general, when I give a talk, I prefer to say where I'm living and what I'm doing. So I'm a postdoctoral researcher, as had been introduced by my friend, Professor Manjunatha, that I'm a postdoctoral fellow at University of California, Santa Barbara, which is in the state of California of the United States of America. And our university, this is a picture, some part of it, which has a very nice gate called Hanley Gate. And the university is located on the ocean. This is the North Pacific Ocean. And this university actually is a quite old university, started in 1944 and have been doing very well in terms of teaching, research, and technology, and not only in science and technology, but also in other subjects which are of non-scientific subjects such as history, humanity, and so on and so forth. And in the last year or this year, there are more than 30,000 students are in different programs, starting from undergrad to PhD or programs in between. It has more than 1,000 faculty members. There are various departments, science and technology, and also from arts subjects. Our department is called Material Research Laboratory, which is in this picture is somewhere here, the ocean, which is, I'm actually, very, very happy to be working here in one of the top 5 material research facilities in the world. And this is a research group here. This is a research group which has around 20 researchers. I'm sorry. We have close to 20 researchers in the group, including undergrad to PhD, postdoc, and my postdoc supervisor, Sharnbasva here. And we have been working on different type of materials. In fact, it's much more interdisciplinary than the group that I was working in Bangalore and before that in IIT Bombay. Well, our university, as I said, have been doing very well, and there are many seminal discoveries made over the years, and some of them have been recognized by Nobel Prizes in last 20 years or so. The first one comes in chemistry in 1998 to Professor Walter Kohn, who discovered a famous tool called DFT, density function theory, that is used by the chemists and physicists and material scientists for predicting properties of materials which are not existing, or they're existing but the properties are not known, and others used to predict structures for the materials which are not known, or the materials are existing but we don't know the structure, how they are composed. And in a few years out, there are another Nobel Prize in chemistry, that is Professor Higgins in conducting ethylene, that is a polymer, and there are parts in physics in different areas of it. The Nobel Prize in economics in 2004, and the most recent one is in 2014, again in physics, for discovery in diodes, P-type nitrides. And I hope you know what is P-type means. P-type means that the conductance is mainly carried out by holes, not by electrons. For this discovery, Professor Suzy Nakamura was given Nobel Prize, but that work was done in Japan in 1980s in a company. So I would recommend all of you to read his life story. That is very, never mind. Yeah, so why this discovery is very, very important, and I like it a lot because I work on optical materials, and optical materials, again, very close to me. The blue LEDs, red, and other LEDs are used for display purpose, and we use at the traffic signal, we use in our mobile. When our battery is discharged, we see the right LED is blinking. When it's charged, we see green LED, and maybe some of the devices we see blue LED is blinking. And other measures, the contribution of this LED is actually going on. It has not fully come to the market, but in some part of the globe, say in US, and I think some countries in Europe, they use light emitting LEDs to lit their houses, street, or wherever we use white light for illumination. But mostly it's not, because there are cost prices. It's too expensive, so we can't bear right now. But I hope the prices will come down and it will be realized in each and every houses. It's just much more efficient than currently what we use is incandescent bulb, which were discovered many years ago. And the current situation in our country is, I think, a mixture of incandescent bulb. I was at white light LEDs. Now there's a question arises here that why, how can we make white light LED out of this blue LED? So the simple answer is we can take two another LEDs, which are green and red. Mixed with this, we have 3 LEDs, and that is nothing but RGB, and it will give white light that can be used for lighting houses. The other, the technique which can be used is coat this LED with another material called phosphor. Phosphors are the famous luminescent materials that actually emit white light. So you can coat this LED with the phosphor, and the phosphor will absorb this light and it will emit white light. So that is the way forward. We can have white light in our houses with almost 10 times the energy efficiency. Yeah, so this university, and we all are living in a city called Santa Barbara, which is very nice city, you know, not crowded and clean, very, very clean streets. And this is surrounded, on one side there are hills, and other side there's ocean, as is in between. You can go to city center in the top of this clock tower. You can see aerial view of the city with the buildings looks like this on the top of it. There are nice beaches, very clean, and you can go on the wharf. This is, I think this is nearly 100 years old wharf. It used to be harbor here, and you can go on the top of, there are several restaurants and there are sightseeing. On the coast of North Pacific Ocean, and we can see large number of aquatic life here. You know, we can go in boats. There are several companies running boats. We can go inside and see these are seal kind of animals called sea lions. You can see several hundreds of dolphins. If you are lucky enough, we can see the whale. I was a little bit lucky, so yeah. So there's beautiful life here around. Well, my relation with Bangalore is deeply rooted in JNCASR, where I started this area called two-dimensional materials. As Professor Manjunath mentioned, that I was a postdoctoral fellow with Professor Rao, who is well known not only in India, but most of the countries wherever science is happening, and having all kind of awards which are possible on this globe. There's a time where my friendship started with Cambridge Institute of Technology. Professor Manjunath worked with me, I think little more than a year, and we have published few papers. Some of them are displayed in the journals of international repute, and they're significantly cited by others. And these articles happen to be on two-dimensional materials. Here you can see phosphorine. I will come to these materials when we go on a technical talk. And this is other kind of two-dimensional material, which is called, actually the chalcogenides is a big family itself. There are hundreds of materials in this family. Well, coming to our the technical discussion, our discussion is on two-dimensional material that's related to dimensionality. So let us first understand what is this all about? What is the dimensionality? What is two? When there is two, there could be one, could be zero, could be three, and all kind of things. So I'm taking a simple example of carbon, which is everywhere, of course. And it has 4 allotropes in terms of dimensionality. Think of first this fullerene, which I hope many of you know because it's in textbook in high schools and college. It's also called, I think, Buckminster fullerene. This is nothing but similar to a soccer ball. Now think of 3 axes, X, Y, and Z. And once you have fullerene in hand, you cannot grow fullerene in infinite direction along any of 3 axes. So that means this is 0-dimensional because you don't have any axis which is infinite long. So come to carbon nanotube, which is confined on 2 directions. You may consider X, Y, Z, X and Y, or Y and Z, or X and Z, it doesn't matter. Along 2 of the axes, it is confined. It cannot be, it's like a tube, but it can be grown in infinity length as long as you have enough carbon and stuff like that. So this is called 1-dimensional because it can only grow in 1 direction. And then coming to the next dimension, that is 2-dimension. So these materials, which I call 2-dimensional, or they're called 2-dimensional materials, they are grown in 2 axes. You consider X, and normally is X and Y, but there is no growth. There is no growth perpendicular to that. So let me take this paper and try to explain you what is it. Yeah. So this paper is analogous to graphene in terms of its morphology, but not in terms of thickness. This thickness is too much if we consider this particular material on the screen. So this paper, it can be grown on this direction or this direction, but cannot be grown on Z direction. So such types of materials are known as two-dimensional material. And then move to the next dimension, diamond, which is well known in market, and we know the structure we used to study in the textbooks. And here, all carbon atoms are connected in all three directions, X, Y, and Z. So this is called three-dimensional materials. So let us confine today to this material as well as the other materials which are of similar dimensionality. So this is called graphene. It's one sheet, but I'll be talking more about it in the coming slides. So this is again graphene. So what is a graphene? Graphene is nothing but one sheet of a graphite, and graphite is something which we all use in terms of, at least in terms of graphite pencil. So the pencil nib is graphite. The structure is again familiar with all of us because we study in textbook in schools and colleges. If you remove one layer out of this several hundred layers in a graphite chunk, that layer is called graphene. But how to do it is not that easy, but I will come to that in some time, that how to separate a layer out of it. But right now, you can compare this with a deck of play cards, which has, I think, 52 or 55 cards. Take one card out, that is equivalent to graphene. But it's not 52, it will be several thousand layers in that, in the graphite chunk. So over last several decades, this area has grown exponentially. There are several reasons for that. First reason is we scientists are curious to look for new materials, and in existing materials we'll see what they are useful for and what all kind of things. Other things, many of them are very, very useful for the technologies which we have today and in the recent past. So over the time that are close to 1,000, I think they cross 1,000 two-dimensional materials, and I would classify them in two categories based on what they are composed of. So the category one is monoelemental 2D material. This word itself testifies that these 2D materials are made, the sheets are made only one type of elements, which we just understood from graphene, that's made of only of carbon. And as you go down this group, silicon, germanium, tin, you will get other two-dimensional materials of these elements, which are by convention with graphene, they are called silicene, germanium, tinine. This "ine" suffix comes from the analogy with graphene. Well, you can move a little bit left and see the boron does the same. Well, it's not stable, of course, but it does form. That's called borophene. And move on the right-hand side in group 5, you see, you forget about nitrogen, which doesn't form 2D materials. Phosphorus to bismuth, they all form single layer two-dimensional materials. Their names are again originated due to their relations with graphene, because graphene is monoelemental and these all other stuffs are monoelemental. I have given in bracket again some of the materials. That means these materials have godfather, that is their bulk layered material. For graphene, we have graphite. We don't have any naturally occurring allotropes which are layered thick material. They are not there for these elements, but we do have for all these group 5 elements which can form 2D materials. So why these bulk materials are important? Because we can take them, they are available in nature, and then peel and get a single layer out of it. And the single layers are extremely important because that's where the two-dimensional nanoscience starts. And because the single layers are on thickness is depending on material is 2 to 3 angstrom. That's it's 1 divided by 10 to the power 9 or 10 meters. So that's a nanoscience, which starts with single or few layer material. Coming to the other categories, compound 2D materials. So these words indicate that in a single layer, it's not made out of one type of elements, but you will have 2 or more than 2 elements in one layer. That's a general definition of compound is you have, it's not allotrope, you have your 2 or 3 or 4 elements. And you have more number of compound 2D materials because it is based on statistics. You have more combination to look into, and we are curious to combine the different things and form different type of materials. So basically, you have more options to do here. You have more choices to do that, and there are materials. Every day you see new materials being invented by combining some type of elements. And Rao's group in Bangalore expert in most of these 2D materials. What is more important to because why many people look for such materials because they're very, very useful. They have several applications in different areas. Many of them are listed here. You can read this review article for your interest. Transport is electric transport because many of 2D materials are electric conductors. So you can use them for charge transport, and some of them also can be used for ion transport and some other type of stuffs. They're extremely useful energy storage, and the best example is lithium-ion battery, which we need. It became almost essential now. Then catalysis, this is again very important area, and 2D materials are actually dominated this catalysis, especially producing hydrogen out of water. And this is very, very hot research area currently. But however, there are no techniques that we can produce large amount of hydrogen today. It will take several years, but I hope it will be realized one day. This is device. Here it is transistor. So 2D materials can also be used for transistor for processor in our smart devices, mobile phone or laptop or things like that. Here it's called thermal. It's generally called thermoelectric. That means several 2-dimensional materials can be used for producing electricity from temperature, from something which is hot. This is opposite to what we see in iron box or heater, where we supply electricity and we produce heat. But here it is opposite. So why we have to first, heat something and then make electricity? No, where this is useful is the heat which is wasted. Like for example, we use a bulb in our house. So why the efficiency of bulb is low because most amount of the energy which it takes goes waste in the heat. It becomes very hot. So that heat can be used by such materials to produce electricity. So that's where this area is very, very important. And magnet, you can make magnet, of course, if you have iron in the layer, or you have cobalt, which have unpaired electrons, which I won't go in the detail because it itself is a large, huge research area, with technologically a very much evolved area. The optical properties are extremely important again, and I love this optical properties, of course. So you can make lasers out of 2-dimensional materials, and different types of things you can make. So it's again huge research area. So what I will do is I will touch upon few of the applications because it's as I said, it's a very huge area and cannot be covered in I would say in several seminars. It needs many seminars. I will be touching upon energy storage, catalysis, and leave the rest for another seminars in the future. Yeah, so I will be talking about energy storage, and I'll talk about 2 types of devices, lithium-ion battery and supercapacitor. And in catalysis, I will talk about hydrogen production from water. In all these, the type of applications, how 2-dimensional materials are important, I will be discussing with example as and when they are required. So coming to lithium-ion battery, I think we don't have to introduce anything about lithium. The lithium-ion battery is only making these things to run. You have mobile phone, your laptop, tablet, digital camera, power bank. This is of course not a device, but we need when we plan a long trip, of course. You have fitness tracker, you have temperature sensor, which is quite a bit used these days to screen COVID-19 patients at airport and other public places. Drone, which is used in surveillance and other applications where you have camera fitted it here and live in the sky. It can take care of some area, can send images to you. So the drone, and then in recent years, the electric vehicle become very renowned technological field. I think in the United States, Tesla is the most famous, but we in India, we have probably I see in Mahindra and Mahindra, and also I think Kia is producing electric cars in Hyderabad, but I'm not sure in the recent, but I know some years ago they had a production unit there. Anyway, they all need battery. So, but today what we have best is a lithium-ion battery, and it's really very, very, very nice. So for us, it's very, I mean, we are not going to give a catalog of what it is, but it's very important to learn how it works and what we need to make its efficiency better and things like that, and what we have to look for in the future, what lithium-ion batteries are not having, which we have to search in other materials. So just see this arrow. The devices on the top are using lithium-ion battery of today, and the devices in this side are powered by batteries, but these are the old styles of batteries. I think some of them like nickel cadmium battery and stuff like that. Well, this is good. There's no problem. We have a lithium-ion battery in laptop, and we are happy with that. But what is next? And we won't stop here. So what is going on today is, people are looking to become smart, wearing smart goggles, smart clothes, shoes, and things like that. And then there are technological projects going on that you have a solar-powered drone. If you have the wings are coated with silicon, the solar cell, there's several solar cells. You can leave it in the sky. It will definitely will run daytime when sun is visible, but it won't in the night. So what you do is you put a lithium-ion battery somewhere in it, and that battery will get charged in the daytime, and it can run in night and day without needing your help for maybe for years. And there's other project by Google called Google Loon, which is again unmanned. So you have a Google, you have a balloon, the self-powered your solar panel and lithium-ion battery. This goes on flying, but I don't know why this has to fly anyway. Well, coming to science, chemistry, which I love a lot, when we talk about any technique or anything, I cannot proceed further without telling the science behind it, the concept behind it. So let us talk about the inside story of lithium-ion battery. So today's lithium-ion battery is made of two types of lead material. On cathode side, you have lithium cobalt oxide. On anode side, you have graphite. Both are bulk. So far, there is no nanoscience. And these are layered material. Look at the layer of the lithium cobalt oxide. Lithium ions are not part of layer, but the layers are made of cobalt and oxygen. So this is how it looks like, where you have a green one is cobalt and red one is oxygen. And how they're connected is, suppose you have, this is cobalt. So you have 3 oxygen on the top here at 120 angle and like this, and 3 in the bottom. So each cobalt has 6 oxygen attached to that, and each oxygen further connect to 2 cobalt in the plane, and it grows in infinity in x and x and y axis, but it doesn't grow on the perpendicular, the normal axis, z direction. So again, it's a 2D material. Graphite, I just explained how it looks like. So now the entire, I would say the hero of the movie is lithium. So let us go to the next slide and see. Yeah, so let me mention here, it's very, very important. This material was made in 1980s by Professor John Goodenough. And I mean, it's a normal discovery at that time, but with time, it so happened that it's become extremely important today. And all these devices are powered with that. And this has been recognized by Nobel Prize Committee last year in chemistry. And that's where he got Nobel Prize after 40 years of discovery of this material. And it happened to be the oldest Nobel Prize today. He happened to be the oldest person to get Nobel Prize at the age of 97 years, and is working even today. Well, so let us see how it works. So I want to show this, flash this video. So the current picture is for a discharged battery, the freshly made battery. When you make a battery, it's discharged. This has rest phase, no energy in that. And let us see when it charges. So lithium ions are moving away from lithium cobalt oxide to anode. Discharging. Now discharging. They are going back to their original location. Yeah. So this back and forth movement of lithium ion, what makes this battery running day and night. You can do several time charge and discharge. And this lithium in the cobalt oxide, they are lithium metal. Moment they leave from here, they leave in form of lithium cation, Li+, and leave the electron behind. Electrons will travel through this circuit to the anode. They're ready here. Moment the lithium ions reach there, they will mix with electron and become metal again. And the reverse happen when you discharge. And you also see there's a blue background here and a separator in between. They are nothing but electrolyte and separator. So let us talk about the 4 parts of the battery. I just mentioned cathode and anode and the separator in between. Separator actually doesn't allow these 2 electrodes, cathode and anode, to talk to each other. If they mix with each other, that's where short circuit. That's the useless battery. What separator is very similar. It is a polythene with pores inside. So through pores, lithium can move back and forth, but that are made in such a way that it doesn't allow electrode to cause a short circuit. And then you have electrolyte. So here the structure of the battery, you have cathode, anode, you have separator, you have cathode, ref them, I mean they stack them over each other and diff them in a container containing electrolyte, and then close with the insulator and can, and you can make it fancy from outside. That's not a science. Electrolyte is nothing but it is required for lithium to travel. It needs a medium to travel. So what in these batteries what is used is lithium hexafluorophosphate. This is the ionic compound, or lithium perchlorate, where you have lithium plus and PF6 minus. And these compounds are dissolved in organic solvents, which are mentioned here, but there are many more. And people also work on different organic solvents to increase efficiency. And here I will leave a question to particularly to a student. And sometime it so happened that lithium ion battery blasts. I think I remember some years ago, there was a ban on Samsung Galaxy 7 because of a few blasts happen here and there. So why does that happen? I will give a hint. Because of there's a problem with separator, the manufacturing fault, and because the separator is not proper. So what happens is electrode, when they're charged, there is a short circuit, and because there is a short circuit, there is a little bit sparking. You will see the little that is sparking, and because the electrodes are dipped in organic solvent which are flammable, and as a result, these solvents will catch fire, and there's a mess inside, cannot bear the fumes, and it will blast. There's one way to do, but there are certain other way where it can cause. But this is the majority of the battery, whichever the blast, this is the reason for that. This application is solely based on bulk. The entire thing is happening between the gap, in the gap in between layers. So let us come to the nanoscience of. I will take one. I don't know whether lithium cobalt oxide has been used for nanoscience. I'm not aware of that. But graphite is a wonderful material to for batteries, but then it is doing much more when you peel one sheet out of it, make graphene and use it. Okay, for college students, I just wanted to put a picture. How can we make one sheet, take one sheet out of graphite? So these are pictures in the sequence they're showing how to do it. Take the sellotape or scotch tape, whatever you have, put a piece of graphite on the top of it, and your adhesive should be on the top, on the upper side of the tape. I can show you. I have, I think, sellotape. So some part of it I can show you. Yeah. So what you do is you take 10 to 15 centimeter long sellotape, put a graphite piece here at the bottom, and then press it like this. It's shown in picture 2. And after that, what you have to do is you just keep pressing like this. It's not all right. Like this, and then separate it. And do 2 or 3 times like this while moving the center, that the fold here and there, not at the same time. And after you see the graphite pieces are thin pieces are here and there, remove the bulk from there. And then keep doing continuously like this several times, like this. What you will see after some time, say doing after 30 or 40 times for a few minutes, you will see very, very thin pieces here and there with light color. That's what is graphene. So then what you do, you take a silicone piece, put in a clean table, and turn it upside down, which is shown in picture here, and press it with the, say I have a silicone piece here, I'll do it like this and press it a little bit with the softest tweezer, and then carefully remove it. Don't allow that silicone piece to come after it. And what it did, it transferred those pieces of small, thin graphene on this silicone substrate, but you can change substrate as per your requirement, what you want. Then go to optical microscope and see, this is how graphene looks like. If it is intense color, it means thick graphene, is not one layer. If you see very, very light color, that's a one single layer graphene. And to confirm that, we take help of atomic force microscopy, which tells you the thickness of the layer. So what it does, it is a cantilever, and the tip, which actually in the tapping more taps like this, wherever there is a seat, it will go like this and then again come down. So this difference will be measured in terms of height in a nanometer or angstrom, depending on how thick it is. Here it is in angstrom. Its thickness is about 0.3 angstrom. And then you go to transmission electron microscopy, which is very, very useful technique for two-dimensional materials. And if you have really one layer, you should see hexagons like this, and that is what graphene, this is recreated here, and graphene looks like. So basically by using TEM and AFM and also the techniques called STEM, such things, we can see graphene actually, and this is really wonderful, and I love it a lot. All right, so this is how graphene is produced, but this technique can be used for many other two-dimensional materials in same way exactly as it is shown on the screen. And this discovery for graphene, it happened in 2004. I think it's a paper here, not visible, somewhere here. This one probably, there's so many things on the screen, I think. Anyway, 2004, by two professors in University of Manchester, United Kingdom, Professor Andre Geim and Kostya Novoselov. They did it first time in 2004, and because the graphene is a wonderful material, so many things came out in a short period of time, say 5 to 6 years, and in 2010, they were recognized by Nobel Prize in Physics for for making graphene. Here is a good looking picture of it. And because it has so many good things, wonderful materials, so this university created 2 national institutes in this university, the Manchester University, for solely working on graphene, its properties, the science related to that, and technology which can come out of it. And these institutes are named as National Graphene Institute and National Engineering Innovation Centers. So huge research going on in these institutes in United Kingdom. And people around work, many people are working on it. And our Professor Rao is expert, his group is expert in it. As I mentioned, these wonderful materials. So what are the properties? Okay, it is the world thinnest material. There cannot be anything thinner than a carbon atom. Carbon atom diameter is something around, I think, one angstrom or so. So that is the real thickness of graphene, because it's a flat sheet of 1 atom thickness. And if you compare with human hair, it is million times thinner than a human hair. Human hair, I think it is close to 0.1 mm or something like that. Depends on whose it is. The high surface area, this is very important. Yeah. So take a graphene sheet here. I consider this as graphene. So the top and bottom surface is actually huge, and thickness is almost nothing. So 1 gram of graphene, the area on the top and bottom, you ignore this area because it's very little. When you have big sheet, it of course become negligible. So the area on the top and bottom for 1 gram of graphene is about 2,600 meters square, or if you split into what I would say is 50 into 50 ground. And 2 gram of graphene you can cover football ground. So think is very high surface area, and it has highly electric conductivity material. Is as good as copper. Sometime if you have a high quality graphene, it will become better than copper. And copper is one of the best electric conductor we use in wiring in houses and otherwise. Graphene also has high heat the conductivity. What does that mean is, take this graphene sheet and warm this side a bit, and very quickly you see the other part of it is warm because the heat is conducted pretty quickly. These properties are not known in many materials. So this is quite unique. And I would say most amazing, most interesting stuff about graphene is its strength. It's the strongest material in the world with Young's modulus about 2 terapascal, or in terms of, if you would like to say Newton meter square, it is 2 into 10 to the power 12 Newton meter square. So I wanted to say a little bit about it, what exactly it is. So what you have to do to see how hard or how flexible your material is, you take graphene sheet. I hope you see this thing what I'm displaying. Stretch it a bit. So I'm stretching like this, and assume that this is 1 centimeter and I made it 2 centimeters. So the change in length is 1 centimeter. So the change divided by original length, it is 1 by 1. So your strain is 1. So strain is nothing but change in the length divided by the original length is 1. When you leave it, it will quickly come back to its original because it's elastic material. The force with which it comes back is called stress, which is a numerator here. The stress is the property of the material. Strain is nothing but we do it. So the stress is so high in the graphene. So moment you stress is make it twice the length of this one and leave it, it will come back with the force that is very high. And how you calculate it is, you find out the force in terms of Newton and then divide it by the area perpendicular to that will give you stress. And then you divide stress by strain, you will get Young's modulus. So there's no other material which is having the greater Young's modulus than graphene. Of course, I think before discovery of graphene, diamond used to be the strongest, which has 1 terapascal Young's modulus. And the other property what it has, and this is there in many materials, when you have seeds like graphene, say in a chunk of graphene, or say a pinch of graphene, there are several seeds. And because the interaction possible between the seed is only a weak van der Waals interaction, wherever you have a weak van der Waals interaction, your molecules or your sheets or your nanotubes or foolery, whatever you have, will have a slippery texture for smoothing the stuffs. Those who are not very familiar with nanoscience can see this dimension. What is 1 angstrom? It is 10 to the minus 9 meters, and 1 nanometer is equal to 10 angstrom. So this is the regime where entire nanoscience work. So your dimensions are few nanometers, so it's a 10 nanometers, or sometimes less than nanometers. And when you have such things, such are in properties, many a times much different, significantly different from the bulk one. Bulk is nothing but what we can see by our naked eyes. Well, moving forward with graphene. Graphene is a wonderful material for supercapacitor. This is a supercapacitor. Have supercapacitor can give n number of supercapacitors is very efficient. It's not there need or a supercapacitor needs. It needs high electric conductivity. It needs high surface area. It needs high thermal and chemical stability. And after listening all these things, graphene will come and say, I have all these abilities. Okay, great. We will use graphene. What is there? So what are the advantages of supercapacitor over battery? That's the best comparison we have. So it has high power density. That means you can draw more energy pretty quickly. It's also the quick charge and discharge in a matter of few minutes. And I was reading on the website, I think given here, they said the supercapacitor of graphene can be used for 20 years for charging, discharging by thousands of cycles. So what are the disadvantages? Is low energy density. So what does it mean is you cannot store a huge amount of energy, whereas you can do that in lithium-ion battery. So suppose you have a lithium-ion battery where cathode is of say 1 milligram of lithium cobalt oxide, and you have anode of say 1 milligram or so. You have some amount of energy stored in. You increase this quantity to 2 milligram to 5, 10, and go on. You will increase the total energy which is stored in the battery in proportion to the quantity. But when you want the lithium-ion battery for your purpose, you can't take the energy out in proportion to what you stored. It will still give energy with the same speed, with the same amount. So you can see these lines coming out from these cups. But the bigger cup indicates that you can store more energy in the batteries. There's energy density. But when you talk about supercapacitor, you cannot store more energy because supercapacitor material has to be as thin as possible. You cannot make it thick and make supercapacitor. That's useless. So when you make a supercapacitor of graphene, one layer means one layer. You can't do anything out of that. So you cannot increase it. But what you can do is you can take out huge amount of energy very quickly out of supercapacitor. So whenever you need, say, a high milliampere per hour, that type of power you need, you use supercapacitor rather than battery. But a lot of research going on because supercapacitor is still young. Again, as I said, it's very important to understand how it works. So it's pretty similar, very cool device. What you have to do for building a supercapacitor is take these two metal plates or metal aluminum foil, rather you can take. These are the metal foils, which are also called current collectors. So these are the plates. And what you do is you coat a graphene layer here, also coat a graphene layer here, and put a separator in between. You can use same separator as it was in lithium-ion battery, and also put not too much electrolyte in between, and then bring them close, very close, as close as possible, but make sure that your separator is nice. There's no fault in that. It should not cause short circuit. Now, when you make it, is again at the discharge, is the rest. Now connect it to power source to charge it. What happens when you charge? That's very interesting. These wool type of things are become things, they are graphene. So when you connect it to the charging source, the positive and negative, the positive terminal will take away electrons from this part and send them to the other side, negative one. What it does, it will leave vacancies behind. Those vacancies are in the semiconductor world, or people who are working in energy, they call them hole. And the hole is nothing but there was an electron and now it's not there. So it's created a vacancy. That's called hole. It has a positive charge, the positive electron. And electrons will come here. And moment that happens, this electrolyte ions, they become active. What they will do, they will travel opposite. So say if you use lithium hexafluorophosphate, your hexafluorophosphate anion will move toward this plate, and the lithium will do the opposite. And once this is done, it is charged. Now you see there are, why they are also called electric double layer capacitor, because you look at this particular portion, there are two layers, one positive and negative, and that's why they are called EDLC. And the thickness should be as, the gap between positive and negative layers should be as less as possible. And I don't think so there's something which can make it better than graphene. That's the thinnest material in the world. So that's why graphene is thought to be the very good material for supercapacitor. And other difference between battery and this, in battery, you store energy in terms of chemical reaction. There's chemical energy which is driven by lithium plus. That's what the entire the game is. But here it's not like this. You have layers of negative ion and positive ions. There is a electric field created here, and that's what make these supercapacitors to store energy. And when you use them, it will go back here. And this is the picture, how it looks like. You stack metal foil and put a graphene layer, separator, this thing roll and dump in a electrolyte. And this company pretty much works on graphene superconductors. So those who are interested can read. They're working on many types of graphene super capacitor. The company is, I don't see the name anyway. Skeleton Tech. All right. So what else graphene does? Because that's solely based on conductivity and surface area. The other property is hardness. That should be used somewhere. And this particular application is because of its slippery texture, of course. So you can use for lubricant admins. Because of its high elasticity, you can use for the stuffs like frames in cycle. A company called Desi.com in United Kingdom selling cycles whose frame has 1% graphene in it, and they say the frame weight is about 750 grams. That's quite low. And then there's a company called Head.com making tennis rackets with graphene in the handle. So I didn't really read the review of flares, but it's said to be very nice. Same company also making skis for diving for ladies, but I don't know why this company is not making skis for boys. They're only making for girls. Also, there's other company making helmets, but the benefit of graphene helmet is thin, light, and comfortable. Other thing is, as I mentioned, graphene is highly thermal conducting. So when you have graphene in the helmet, the heat gets generated in the head when you are wearing a helmet will quickly go out, and it will get dissipated in the environment. So that's a very nice property of it. And there are other things with that. Of course, it's expensive. I think a few $100 probably. The other property, graphene makes rubber more rubber. This is interesting. So natural rubber, what we have latex. If you mix a graphene, the practical this experiment is done. The group again in Manchester, mentioned here at the bottom of it. What they did is they made a rubber band of latex. This is natural rubber, and mixed some graph amount, maybe I think few percentage, and made it like this, and then entangle this here and do this experiment. See what is happening. You can. I would like you to watch this video. So what essentially is happening is it becomes more strong when you mix with graphene because of its elasticity. But at some point of time, it will break because you cannot do too much. So basically, with this invention, what you can do is the items which are made out of natural rubber latex, you can make those items more strong and also thin because they're strong. So you don't have to put too much rubber on this. The latex glows. And pretty recently, few years ago, this Bill and Melinda Gates Foundation gave a lakh of dollars to this Manchester University to make new generation contraceptives, which are again thin and strong, supposed to, but they're not in market, I think. And the other company which is selling tires, it's called Vittoria. So they say there is a few % of graphene is there in the rubber which is used in tires, and the tires are very strong and puncture proof. So that's fantastic. And I wish I could have bought it before this pandemic kicked in, because I have 2 bikes and both are having flat tires now. So I can't go out and get, because the shops are not open. Anyway, it doesn't matter. Another application of graphene, which is still at research level, there's no technique has come out, to filter out useless ions from dirty waters. And this process is of course known as desalination. We use in everyday life at our houses a technique called RO, this is reverse osmosis. This the opposite to the osmosis with natural process. So graphene and some other materials might replace this technique in the future. So there are some papers which I'm showing pictures from them. So look at this graphene sheet. There are holes, they're of nano size, maybe 2 or 3 nanometer, or maybe I think less than a nanometer. You create these holes and then pour water on that. What it will do, it won't allow this other ions which we don't need to come down. They will remain on their own side. Other one which is even more efficient, you can oxidize graphene to make graphene oxide. In fact, graphene oxide is another very, very nice material, which is well studied over the years, and many techniques will come out. This is again beautiful material, product of graphene. But however, what you're doing in graphene oxide is you're oxidizing graphene. The sum of the carbons will become sp3 hybridized. In graphene, all carbons are sp2 hybridized. So when you do this, some carbons here and there will become sp3 hybridized, and they will connect with oxygen here. So it become epoxide. I would say, I'll try to explain. Say pick 2 carbon on this one. So oxygen here, and this connects here, epoxidely. That's what is graphene oxide. But I think percentage of oxygen is little, maybe less than 10%, I guess. So when you have that, when the graphene sheets come closer, there's a more gap because there's oxygen in between. So you have huge channels, and you can pass dirty water through it. The ions which we don't want will remain on one side, and water will pass through the channels, and you will get pure water for drinking. So it will take time. We will wait and see what comes out. Anyway, so I'm now moving to catalysis, which is again related to energy, but it's not related to the devices. So this concept is actually not new. A couple of centuries ago, in a fiction novel by Jules Verne, The novel name is The Mysterious Island, published in 1874. It's available at this link. If you're interested, can read it. Somebody asks the author that what we will do once this that organic fossil fuel gets over. So he writes in his novel that I believe that water will one day be employed as a fuel, that hydrogen and oxygen, which constitute it, will furnish an inexhaustible source of heat and light. The water will be the coal of the future. So why does he say like this? Because water has hydrogen and oxygen. If we break water in H2O and O2, we can use hydrogen as a fuel, and oxygen we don't care, it can go in atmosphere. Why hydrogen? Because hydrogen has high energy density compared to what currently we are burning. I have drawn methane here, but the different fuel, for example, LPG contains, I think, propane, and diesel contains some longer alkyl chain alkanes, petrol contains something else, but they all are alkanes. And it doesn't matter whether it's methane or what, but the product remains same. So if you have not burned it properly, if you have not supplied enough oxygen, you may get carbon monoxide that is hazardous for us. I think it causes some diseases. And along with that, it produces heat. That's what we use for running engines and thermal power plants and whatever it is. So there are, of course, there are many disadvantages of fossil fuel. The first thing, the worry of everyone is it will get over on some day. Other thing is it creates pollution in different ways. So if you look at hydrogen, it is clean burning. There's no product, only the dangerous product, only water, which is our friend. And along with that, it generates heat, which is much more than what is generated here in terms of, you say mole or you say gram. This is much more per gram of hydrogen compared to the per gram of methane or other organic fuels. So advantage of hydrogen fuel, high energy density, and there is no pollution. So let us look at the reaction through which we can produce hydrogen. So the problem with hydrogen is, let me mention here, we don't have enough hydrogen. It's beautiful material. So it's a kind of fantasy so far. One way, as in the previous novel it is told, and many people may think, thinking it may be possible, is to break water in hydrogen and oxygen. But this reaction, is fortunately or unfortunately, is actually energy expensive. To produce 1 mole of hydrogen, you need 237 kilojoule energy. That's quite a bit. Who will give that? And not only that, this reaction to occur, there is a tall energy barrier, activation energy. You need something to cross this, and you need another energy which actually will not be consumed, will come back, but you need to provide that to cross over this hill to come to this level. And it has been well studied over the years that two-dimensional materials can do both, reducing this height as well as take energy from some other source and supply it to this reaction so that this product can be formed. That's why the fact that they're actually lying above the level of water. That's what the difference here. Let us go to the further detail of this reaction. This making hydrogen from water is actually a redox reaction where oxidation and reduction both happens. In oxidation reaction, you get oxygen. In reduction reaction, you get hydrogen. That's what we need. We don't worry about oxygen. But we do need these two the stuffs to combine together and give hydrogen. That's what is the reduction. Overall reaction is like that, where you have written energy requirement in terms of voltage. Now you may say whether you write in voltage or in kilojoule, what difference it makes. It doesn't make any difference. It needs same amount of, it's just a conversion. And you can see how it is converted. So let us look at this reaction, the same reaction basically. So for 1 mole of hydrogen, you need this much of energy. That means for 2 moles of electron, because to produce 1 mole of hydrogen, you need to consider 2 electrons. So for 2 moles of electrons, you need 237 kilojoule energy, or 237 and then 000. I removed K from that, this much energy for 2 moles of electron. And I think all of you know it, but the number is 0.023 into 10 to that is, so 2 moles of electrons will be equal to 2 into this number of electrons. So per electron, you will end up with energy requirement 10 to the power 19 joule. So what it says is, to take part in this reaction, you need to provide that much energy. A volt, the energy divided by charge on electron, because the entire game is of electron, you will end up with, through this calculation, in 1.23 electron volt. Whether you write electron or not doesn't matter. We are writing because indicating all the entire thing we have done is for electrons. So it's the same thing as writing 1.23 volt. And the negative sign here says that we have to give volt. So this is a convention. There's opposite in energy. When you're negative here, it means energy is released, but positive means is given. But in terms of voltage, we write opposite. Anyway, this problem, as I mentioned, 2-dimensional materials are solving and will solve to the greater extent. And this can only be done by semiconductor 2D material. So I will tell a bit about semiconductor. This term is coming first time in this talk. So far in the previous slides, I told about certain structures of graphene and stuff like that. Those structures are chemical structure, where I shown atoms are connected by bonds and where they are lying in seed. There's another structure called electronic structure. What does that mean? In a seed, you have several atoms. Each atom has got some number of electrons depending on what. For graphene, you have 4. So these electrons, after material is formed, they will join hands together and will form their own levels. Their story is called electronic structure. What they normally do, they will join together and form 2 energy levels with a certain gap depending on what material it is. A level below is called valence band, and the level above is called conduction band. How do you remember? You come from the top, A, B, C, and go down. So C comes first. On the top, it is conduction band. To remember it, otherwise, the valence band means you have valence electron field in that. Conduction band is empty, but if you fill electron in them, the electron will be mobile. Well, that's okay. I hope you understood that. Now, if this gap, what is created in a material, is equal to or more than 1.23 volt, or the energy equal to 237,000 joule, and you have such material with this gap, the gap equal to that, and these electrons in the valence band are given enough support so that they can jump to the conduction band. And if they are able to jump, it means definitely they got that energy. Where they got, we'll talk in a while. Once these electrons, now I'll tell here, once the valence electron, they were here and somebody jumped to this level. Now these electrons have that energy, what was given by some source. Once any electron has that energy, which is more than this value, that electron should do this job, should give hydrogen if that electron is thrown in water, dumped in water. Well, so what we need is semiconductor. Band gap, this gap is called band gap for semiconductor. And it has to be more than 1.23 electron volt, or if you want to call it in terms of joule, 237,000 joule. There are many 2-dimensional materials which form a structure like this. And in my opinion, best way to do this is use sunlight. Excite your, take a bucket of water, put your 2D material in that, and expose to sunlight. Sunlight has that energy. Your electrons in valence band will absorb that energy and jump to the conduction band. And once the band will have that amount of energy and will do hydrogen production, they don't need water because they're already, as I said, we dumped in water. And why sunlight is the best? Because free of cost, we don't have to pay anything. But same thing you also can do in a cell, in an electrochemical cell, but where there you have to apply voltage. Apply voltage means you have to bring voltage from somewhere. So basically you are giving one energy and taking other energy. That is give and take. But here is the sunlight is free of cost available, and you need right wavelength. And once it is created, you are done. And here H plus means again as hole, as which I told in the battery material. So after they are created, the holes and electrons both move in these bands. They have to move. If they don't move, your material will be called as insulator. That's useless for this purpose. So they have to move. They have to be mobile. So these electrons will move in the band called conduction band. This M is nothing but minima. This is minima, and the minima here. So don't worry about that. It's a conduction band, and so they will travel across the material. And if they travel more, is the best. Now the one may ask whether the solar spectrum which we receive on the Earth, it has the energy which is required or not. Of course it has. Just look at the solar spectrum which we have on the Earth on a sunny day. So this energy or that energy, this energy, whichever it is, correspond to nearly 1,000 nanometer. And this entire spectrum we see on Earth. So we have that. And here I wanted to mention one more thing. You can't have a semiconductor whose gap is less than this, but you can have more. As long as you are increasing gap, and as long as it is fitting to the solar spectrum, you are all right, no problem. Your semiconductor should work for hydrogen production. So if you increase, say, for example, 3 electron volt, that will be corresponding to 400 nanometer here. And this falls in visible light. So any semiconductor between 400 to 800 nanometer, we will call the catalytic reaction done by that semiconductor as visible light photocatalysis. And it's also more useful because you look at this spectrum, we have more visible light. Of course, we have IR and NIR also, but visible light is in plenty. But we always worry about this part, around 250 nanometer. That's very, very dangerous for us. It damages our DNA. So we have a great friend called ozone somewhere in the sky. So we always pray for good health of ozone. So what ozone does is, probably I think it doesn't allow wavelength below 280 or 90. I think so about, but surely 250, it doesn't allow. More you are exposed to 250 nanometer UV light, which is called short range UV light, your DNA will be damaged. There will be mutation which are lethal, and there will be health problems. So we are always scared of short wavelength UV. So I always pray for ozone's good health. Ozone should remain intact. There should not be any hole in that. All right. So now there are a large number of two-dimensional materials which can do this job, produce hydrogen from water, because they have band gap larger than 1.23 eV. And some examples, transition metal dichalcogenides like MOS2, MOS2, Se2, and so on and so forth. Actually, there are many numbers and very beautiful materials that look structurally similar. I draw one sheet of MOS2, and this is bulk. So MOS2 again has its bulk godfather. Peel one, use it for your application. You can also make transistor out of it. Of course, they are not very efficient, but you can do that. The one is again mentioned here, the band gap of MOS2. So it should do that job. Yeah, and it's known. And in Professor Rao's group, there are many discoveries about it. You can also make a composite of graphene and molybdenum disulfide, which also does very well when you put in water. But not to mention that graphene, unfortunately, doesn't do that. What the reason is, let me tell you. Graphene, when it forms band, the VBM and CBM, but they don't have gap. They're actually talking to each other. They're touched to each other. So basically, electrons in VBM and electrons in CBM have no energy difference. They're same. So it cannot do that. And such type of materials are also called semi-metals. They are not called semiconductors or insulators. They're called semi-metals. But they are not metal, but they are not also semiconductors, so semi-metal. All right, I won't bother you about this dye sensitized, but in very quickly, I would say, if your material is not absorbing huge amount of light, what you do is you put organic dye in that. Organic dye will absorb light and transfer to your 2D materials. And so in that way, you have more energy absorbed, more electrons are excited, and they will do job much faster than an absence of dye. So this is called dye sensitized photocatalysis. This is again the well-known research area. Well, we have done several studies in my postdoc tenure at JNCASR. We made a material called phosphorin, which I shown in the beginning. This is a one-layer material, single-layer material of phosphorus atoms. There is no other element in that. And of course, as I said, if you have one layer, you can put under electron microscope and see where atoms are there. This is how it looks like. So you have a phosphorin sheet, and you put electron beam perpendicular and see the diffraction pattern and recreate the picture. You should see like that. And there's I think less than I scale here the 1 nanometer. Yeah, it's also 1 nanometer. So basically, you can see atoms. And again, we make phosphorin out of bulk. Is a non-allotrope of phosphorus called black phosphorus. So you peel it. So phosphorin you can peel in two ways, which I shown in graphene. The other way, which is much more efficient, and I would like this to be, I like this more because you can produce more amount in that. In that the sellotape, you cannot produce huge amount because, of course, it's high quality, but it will be only few layers, very little amount of material. Here, what you do is take organic solvent or water in some cases, but in phosphorin, you have to take organic solvent, dimethyl formamide, or other solvent called NMP, N-methyl pyriledone, something like that. And then your black phosphorus crystal, chunk of it in the solvent and apply ultrasonic radiation. There's an instrument available. What ultrasonic radiation does, it breaks the weak van der Waals interaction which exists in all these 2D materials. Why it breaks? Because the energy which comes out in terms of ultrasound is just enough to kill this interaction. Once this interaction is gone, your sheets are free, and what they will do in the solvent. And this is the actual picture here. So before there was no phosphorin in that, it was colorless, BMF colorless. And once phosphorin sheets gone, you see it's dark color. So this is the way you can produce the large quantity, and chemists like me needs large quantity because with sellotape I can't do chemistry. Well, there's no end to that actually. What else you can do is take phosphorin sheet, take molybdenum disulfide sheet, connect them by chemical bonds, and make heterostructures or nanocomposites. These are composites, we call composites, or people call heterostructure, because you mix two different types of two-dimensional materials. And connecting them by a real bond, we did first time a couple of years ago. And this material shows much more hydrogen production than pristine phosphorin. But pristine phosphorin does show hydrogen production because it has band gap around 2 eV when it is really one layer. But when you increase number of layers, this band gap decreases. That's true for most of the 2D materials. Well, with this, I'll end my talk. It was a real pleasure to be talking to you.
So thank you so much for your presentation, sir. The session was very informative for all of us, especially those who are beginning their PhD as a career. Now our principal has joined the session now. Welcome, sir, on behalf of Department of Basic Sciences. We welcome our principal, Dr. Suresh L, to this national webinar. So we all Cambrians are fortunate enough to work under our able leadership of a principal, Dr. Suresh L, who sets himself as an example to all of us and motivates us to achieve more. So our principal has joined the webinar right now. May I request a principal to address all the participants?
First of all, I would like to extend congratulations to the Basic Science team. And also I would like to appreciate the efforts Mr. Pratap Vishnu has taken. And also I would say I have attended, I have seen his slides and his material. And also I was just going through the chart option where all the participants were demanding these presentations and then his PPTs. That shows the participants are very happy. So, Dr. Pratap, we are very happy to have in our webinar and also sharing your expertise. And even though you are more than 5,000 miles away from us, but you are physically you are not with us, but logically you are connected. And then and we look forward for more and more interactions, and especially always, and always it is a dream. Yeah, always it is a dream for all the researchers. Once in their lifetime to reach California and then and US, and then they can work for the renowned university. And now today they are all very happy because you shared your expertise, you shared your your mind, and also you shared your art to all our participants. Very thankful to you, Dr. Pratap.
May I request Professor Yashoda from Department of Basic Sciences, Department of Physics, to please present vote of thanks.
Yeah, thank you, madam. Thank you, madam. Good morning, one and all present here through online. The best and beautiful things in the world cannot be seen or even touched. They must be felt by heart. Thank you is one such prayer among them. I, Yashodama, Department of Physics, Cambridge Institute of Technology, consider it a great privilege to propose a voice of thanks to all the dignitaries who have witnessed it as a memorable and successful national webinar on two-dimensional materials for diverse application. Today, my words are not enough to express the gratitude on behalf of our college. I would like to thank our chief guest, Dr. Pratap Vishnu, who graced us with his thoughtful, provoking address on graphene materials. It has set a perfect platform for our colleges. I would like to thank our chairman, sir, D.K. Mohan, sir, and I would like to thank our beloved principal, Dr. Suresh L, for all words of wisdom that radiates a source of energy within us. We will never remain grateful to you, and we thank you for being with us today. I would like to thank, and also I extend my thanks to Dean Basic Science, Dr. Shanti SR, and Dr. Pushpalata, HOD, Department of Physics, for support and effort to make this national webinar a great success. My artful thanks to goes out all heads of the various departments and the faculty for their valuable guidance and encouragement in all our efforts. And also I would like to thank and I extend my thanks to Professor Manjunath, convener for this national webinar, for his support and effort to make this event a great success. I thank all faculties from other colleges and also from other places and the participants around the world who witnessed this national webinar. Last but not least, I thank you, my dear students, for your cooperation in making this webinar resounding success. Once again, I thank you all.